Automotive engineering has abandoned scattering hundreds of separate electronic control units throughout a car. Today, these systems are collapsing into centralized computing brains. Consolidating hardware onto a single system on chip strips heavy wiring harnesses out of the vehicle and allows manufacturers to push seamless over-the-air software updates to the entire car at once. But this integration creates a mixed criticality environment. You are forcing completely different software domains to share the exact same hardware resources, processors, and memory arrays. On one side of the processor, you have standard quality management applications, like the cabin infotainment and Bluetooth audio. On the exact same silicon, you have ASIL D safety-critical software, the algorithms that physically steer the car and deploy the brakes. Housing these extreme opposites on a single piece of hardware introduces a severe structural vulnerability, where a glitch in a low-priority app can directly threaten the systems keeping the driver alive. If an infotainment application crashes or encounters a pointer error, the shared architecture means that error can bleed across memory partitions and corrupt the critical operations happening next door. We call this a cascading failure. A bug in the audio app causes a memory overflow, rapidly overwriting the brake controls and paralyzing the system. To prevent this, ISO26262 mandates freedom from interference, guaranteeing a provable separation between software elements of varying safety levels. Proving this separation manually across millions of lines of code and thousands of hardware pin connections is beyond the capacity of human review. Legacy document-based engineering and standard diagramming tools cannot handle this complexity. Their ambiguous text labels and lack of mathematical rigor mean you cannot trace exact dependencies or predict the physical impact of a design change. To guarantee human safety in these modern vehicles, the industry is abandoning static diagrams in favor of formal, mathematically provable modeling semantics. Systems Modeling Language version 2, or SysML v2, addresses this gap. Instead of drawing pictures to represent a system, SysML v2 builds an architecture entirely on formal, machine-readable logic. To guarantee architectural isolation, you have to rigorously define the safety requirements of every single component interacting inside that system. Older modeling languages relied on loose stereotyping to categorize parts. SysML v2 replaces those with structured, domain-specific semantic metadata. The core safety classification framework here is the Automotive Safety Integrity Level, or ASIL. This ranks components based on their critical risk to human life, moving from standard quality management up to the highest risk category, ASIL D. By injecting this precise metadata into the code block, the safety level becomes an intrinsic, queryable property of the component itself, rather than a loose note written in the margin. Historically, critical safety requirements were buried in isolated text documents, completely separated from the actual engineering models and hardware schematics. Utilizing this metadata structure transforms a static picture of a system into an intelligent, actively queryable database of strict safety parameters. With the components categorized, we can establish the first dimension of the freedom from interference mandate, spatial isolation. This model maps two memory domains on a number line, proving a lower-level application's allocation never overlaps a critical space. SysML v2 encodes this boundary using a mathematical constraint definition. A requirement definition links this to metadata, automatically activating the boundary when safety classifications differ. Integrating this Boolean equation directly into the design makes the spatial boundary an active, executable part of the system architecture. If a systems architect accidentally assigns overlapping memory addresses during a routine software update, the system does not wait for a human review to catch the mistake. The modeling environment will instantly evaluate that Boolean equation, flag the mathematical contradiction, and refuse to validate the design. Shifting from descriptive diagrams to active, executable constraints provides the mechanism for achieving compliance by construction. The second major threat factor is temporal interference. This occurs when a low-priority task hogs processor time and delays a critical function from executing. SysML v2 features native temporal syntax. Engineers can model time slices, duration values, and processor scheduling directly into the architecture's code. You can write a temporal constraint equation stating that the combined execution times of all shared tasks must never exceed the system's strict fault-tolerant time interval. The third threat factor is communication interference. A localized network failure or a babbling node could spam the main data bus with excess traffic, blocking critical signals. Engineers can lock down network ports by binding maximum bandwidth limits and end-to-end data protection rules directly into the system's connection definitions. The vehicle's physical memory space, its processor execution time, and its internal data flow are now entirely enclosed by rigid, verifiable mathematical fences. Defining individual constraints secures the local boundaries, but you also have to hunt for hidden systemic vulnerabilities across the entire network. This is the domain of dependent failure analysis. You have to track the invisible domino effects of a single point of failure as it propagates through a highly complex vehicle architecture. SysML v2 utilizes a standardized REST API, allowing the massive architecture file to be instantly exported and serialized as a structured JSON data file. This raw data is parsed into a directed acyclic graph. A yellow data flow originates at a low-level node, traveling toward a critical node. The algorithm scans this web for any path lacking a safety firewall. Unprotected paths are instantly flagged as viable cascading failures. This dependency tracking script runs seamlessly in the background during the absolute earliest phases of software design. Deploying this automated search mechanism eliminates the blind spots inherent in manual safety reviews, instantly identifying structural flaws that the human eye could never process. The ultimate goal of this engineering process is proving the system works flawlessly before a single physical microchip is manufactured. We execute this proof using an SMT solver, an advanced mathematical reasoning engine capable of evaluating all the complex SysML v2 constraints we established earlier. The solver rapidly calculates every conceivable state variable across the model to ensure absolutely no mathematical counterexamples or logical contradictions exist within the design. Passing this rigorous computational test definitively proves that the architectural logic complies with ISO26262 mandates. Formal verification validates the functional safety of the architecture by exhaustively checking every logical state defined in the SysML model. Proving the static math is essential, but we must still observe how the system dynamically reacts across time and physical space. Through the API connection, the mathematically verified SysML v2 model is pushed directly into dynamic execution simulators, like Simulink. Here, engineers execute virtual fault injection tests. They can intentionally trigger a catastrophic crash in the infotainment processor to monitor the fallout. Inside the simulation, we can watch the critical braking controller isolate itself and seamlessly transition to a safe state within the required time limit. By adding FMI protocols, engineers can run co-simulations that introduce real-world physical hardware degradation, like voltage drops or thermal limits, alongside the software logic. By establishing this digital thread, engineers can embed safety constraints directly into the design, identifying interference paths during the modeling phase rather than discovering them during hardware integration.